Okay guys, this is the second video that I'm doing for Biochemistry Colloquium 1 for semester 3. And we're going through lipid synthesis in this video, including acetyl-CoA transport, glycerol synthesis, and then some pathways for amino acids as well as the urea cycle. So starting with the lipid synthesis, we of course have to use acetyl-CoA for the lipids that we're creating. Why? Well, if we go back into the beta oxidation, we can actually see that for every two carbon atoms that we break off, we get one acetyl-CoA. So pretty much fats are made out of several rows in a chain of acetyl-CoA. And that is why we need acetyl-CoA to be transported from the matrix of mitochondria into the cytosol in order for fatty acid synthesis to occur, because this occurs in the cytosol. Meanwhile, acetyl-CoA is made in the matrix of mitochondria. Remember from colloquium 2, I think, the pyruvate is decarboxylated. Decarboxylated into acetyl-CoA. And this is done inside of the matrix of mitochondria. So that's why we need to use this shuttle right here in order for us to transport the acetyl-CoA from the matrix of mitochondria into the cytosol. Now, what are we losing in this transport? First of all, you can notice that we might be losing NADH plus H plus. However, we're really not, because it kind of equalizes here. So we're gaining one here, but we're losing one here, so the net will be 0. However, we do see that we're gaining this NADPH plus H plus, and this, guys, is very important for any sort of lipid synthesis, whether that's cholesterol, whether that's tags, whether that's fatty acids that we're trying to make. This is an important coenzyme that we're using in order to make it. So that's why when we see this circle right here, we see this inner circle, right, that goes like this. And you can ask yourself, well, why doesn't it just use the malate shuttle right here and then go through the protein like this? That is because it wants to create as many of these NADPH plus H plus as possible. 50% of it is necessary for the fatty acid biosynthesis. So that's why instead of going from the oxaloacetate down into malate, we're actually going from the malate to the pyruvate and using the pyruvate to go through into the matrix of mitochondria. Now, another important fact that we have to note is the citrate right here. Now, citrate, if you don't know, is part of the citric acid cycle. We can see it right here, right? And this citrate actually is a good indicator for when we're going to use fatty acid synthesis. If we have acetyl-CoA here, it's going to feed into the citric acid cycle, creating a citrate from oxaloacetate, right? And then the citrate is going to continue to isocitrate, etc., etc. And then this is all in order to make all of this ATP. However, ATP is some sort of allosteric regulator. So it will say if there's too much ATP that we're having in our body, too much accumulation. Remember, we can't have too much ATP in our body. ATP weighs a lot. It will tell our citrate right here to stop being converted into isocitrate. We just don't need the citrate anymore. And instead we're accumulating acetyl-CoA because, again, we have glucose up here and it goes into glycolysis, right? And it creates acetyl-CoA. So we're accumulating acetyl-CoA and we're also accumulating citrate because the citrate is told to stop pretty much. And then instead of the citric acid cycle, the citrate will take this acetyl-CoA that we get from the beginning of the citric acid cycle, and then together with oxaloacetate, it will create the citrate. The citrate will now go through the matrix of mitochondria into the cytosol and then give away this acetyl-CoA. It pretty much says, here we have too much of this acetyl-CoA, just take it, do whatever you want with it, we don't need it anymore. And then it just bounces back into the matrix of mitochondria in this way, actually. Pretty much almost like a daycare for acetyl-CoA. It has too many children and doesn't want to take care of all of them, so it's giving some away, right? And that's our requirement for fatty acid synthesis, because what you're going to notice is that we need a lot of acetyl-CoA in order to create fatty acid synthesis. And that's a lot of potential ATP that we're losing. That's why in order for fatty acid synthesis to occur, we have to have a precondition that we have too much ATP going up here, meaning the citrate will be triggered, taking the acetyl-CoA instead of going into the citric acid cycle, going into the to the cytosol and giving away the acetyl-CoA. All right, for the fatty acid synthesis, there are a few things that you need to know. First, well, actually, very easy. Fatty acids look like this, right? Kind of like mountainous landscapes. And then for every two of these carbon atoms right here, we have one acetyl-CoA, just like we did right up here. This is a good example. Right up here, for every two carbon atoms, there's one acetyl-CoA. So the acetyl-CoA are represented by these pink circles right here. So in order to make the fatty acids, we of course need the acetyl-CoA. So here I drew this little guy right here. This is our ACP molecule. It's our acyl carrier protein. So what this ACP does, it holds an acetyl-CoA in its right arm, you could say. And then in order to create this big chain of fatty acids where it adds 1, 2, 3, 4 acetyl-CoA, it needs to first convert those additional acetyl-CoA into malonyl-CoA. What does this mean? Well, our first acetyl-CoA is going to be sort of normal. It doesn't need to be transformed into anything. It fits perfectly as our first two carbon atoms in this fatty acid chain. So it's just perfectly snug right there. It's part of the ACP molecule's right arm. But then when we get to the other carbon atoms right here, these are still technically made up by more acetyl-CoA. However, we need to now transform the acetyl-CoA because you can technically say we're using the left hand of the ACP. And the left hand of the ACP is a little bit more discriminate. It can't accept just normal acetyl-CoA. It needs for acetyl-CoA to be transformed into this molecule right here called a malonyl-CoA. So this is still technically an acetyl-CoA. It's only transformed, almost a charged acetyl-CoA, you could say. In order for a continuation in this buildup of fatty acid molecules. So the first two carbon atoms in the acetyl-CoA or in the fatty acid molecule will always be a normal acetyl-CoA that is not transformed, but the other carbon pairs of the fatty acid molecule will be this transformed acetyl-CoA called a malonyl-CoA. So the first rule that you have to know is that the first acetyl-CoA of a fatty acid chain doesn't need to be transformed via carboxylase reaction. But every subsequent acetyl-CoA does. So every other carbon atom pair that we have, we do use acetyl-CoA, however, we have to transform it into malonyl-CoA first in order for it to then be added into this chain. And this transformation is called a carboxylase reaction. We transform the acetyl-CoA into malonyl-CoA in order for this little happy guy to be able to just stick the malonyl-CoA into the acetyl-CoA. What is it? Huh? And in order to do this carboxylase reaction, we have to use a number of reactants. Number one is biotin. If you hear anything related to carboxyl groups, you will almost always use vitamin B7 or biotin in the reaction. Number two is ATP. For every acetyl-CoA that you have to convert into malonyl-CoA, you have to use one ATP. And then, of course, you need an acetyl-CoA in order for the conversion to occur. And this will create the malonyl-CoA, which looks like this. And what happens here is the carboxylase reaction. So we have this big B7 molecule, and then we have the ATP here that's turned into an ADP. And sorry, my cat is being a little bit crazy. And this reaction takes acetyl-CoA right here, and it adds this carboxyl group into the acetyl-CoA, creating this malonyl-CoA. And this malonyl-CoA is now this transformed acetyl-CoA, which can be used by the ACP molecule in order to add into the fatty acid chain molecule. Alright, that was the carboxylase reaction. Now we actually go into the real fatty acid synthesis, which is a complete reverse of what we did with beta oxidation. What is beta oxidation? We're taking a fatty acid and we're breaking it down into acetyl-CoA. But with fatty acid synthesis, we're taking acetyl-CoA and we're not breaking it down, we're building it up into fatty acid chains. So it's a complete opposite reaction of what we're doing with beta oxidation. Here we have the malonyl group right here, and here is the acetyl group, right? And this is the little guy that I drew right here. It's represented by this brown dot. So he's holding this malonyl group right here as his left arm, and this is his right arm where he's holding the acetyl-CoA. And the acetyl-CoA can easily be morphed into this malonyl-CoA, creating this first, I would call this a beta-keto acyl, beta-keto acyl ACP right here. An ACP because this little guy is called an ACP. And here we're actually getting rid of a carbon dioxide group, so we are decarboxylating, I think it's called. And this is a signifier that when this goes out of this reaction, this first reaction, we immediately know that we're dealing with some sort of release of carbon atom, because here 1, 2, 3, 4 is the total amount of carbon atoms we have up here. Well, here 1, 2, 3, 4, 5 is the amount of carbon atoms we have there. So it's a big signifier for us to know exactly what kind of reaction we're looking at. So this first reaction is called a condensation. A condensation, of course, because we're getting rid of a carbon atom. And we have a malonyl-CoA as well as an acetyl-CoA, and the products we get is this carbon dioxide molecule as well as a beta-keto acyl ACP. It's very easy to recognize this beta-keto acyl ACP because the beta carbon has a ketone group. Meanwhile here, this represents pretty much what we just looked at for the first step. So instead of having these as a product, this will be our reactions for the fatty acid synthesis. But here they are the products, and then they are turned into this beta-keto acyl-CoA here, while here they're turned into this beta-ketoacyl ACP here. And ACP again stands for this molecule. It just pretty much says that this guy is still holding on to these molecules, right? And here we can see another signifier that for this we're actually introducing carbon atoms into the molecule, while here we're getting rid of carbon atoms from the initial molecule. Next up is the reduction phase, and reduction of course means that we're adding H or hydrogen atoms into our molecules. That's what reducing means. Well, the opposite of reducing you might think it's oxidating. That is also correct, but we could also call it dehydration, where we're getting rid of hydration or hydrogen groups from the molecule. So here, for example, we have this one and this one that we get rid of, and we are left with the ketone group. Well, here, for the reduction phase, we have this ketone group initially, and now we want to reduce it by adding hydrogen atoms, which we do by adding this NADPH plus H, and we add 2 hydrogen atoms into it, and this represents what we also get from here, which would be the beta-hydroxyacyl-CoA. Only here would be beta-hydroxyacyl-CoA, also ACP, I would say. Okay, that's the reduction, and you can see here, as like I said, it's NADPH plus H plus as a cofactor, and this is extremely important because like we saw up here, we're using this other shuttle, almost a new pathway. Instead of going through like this, we're going through like this because we want to create as many of these NADPH plus H plus as possible, because we're now starting with fatty acid synthesis. So that was our reduction. Next up is the dehydration, and this is of course the opposite of the hydration phase that we have here. Dehydration is made by getting rid of H2O molecules from the initial molecule. So we're getting rid of 2 H's and 1 O. So this H we're getting rid of, this H and this O. And we're getting this molecule as an end, also known as an NOL ACP. Also, I haven't gone through the enzymes yet, but of course, in order to make beta-ketoacyl ACP, we need beta-ketoacyl ACP synthase, and then in order to reduce the beta-ketoacyl, we need to use beta-ketoacyl ACP reductase, and in order to dehydrate the beta-hydroxyacyl-CoA, we're using beta-hydroxyacyl ACP. I'm pretty sure it's supposed to say ACP here. ACP. Excuse me. ACP. We're using the beta-hydroxyacyl ACP dihydratase, and we're creating this NOL ACP. And then finally, for our final reduction, which represents this opposite of this dehydration, and we use another NADPH plus H plus. It's another reducing enzyme, which would be the NOL ACP reductase. Here we create saturated fatty acids right here, and it is the only type of fatty acid that we synthesize. Now remember, saturated meant that we don't have any double bonds when we're doing the fatty acid molecule. So it only looks, I've completely forgot how these look like. I think it's like this. That looks horrible, but yes, I think it's something like that. It doesn't have any double bonds. It only has the straight saturated lines, right? Also, the longest fatty acid that we can make with this method, we can of course make longer, but with this method specifically, is a palmate, also, which is 16 carbon atoms long. So that's all for this slide. The next slide is calculation, how we calculate for the amount of ATP that we're technically losing by making a fatty acid molecule. So first of all, we need to calculate the amount of, let's see, amount of acetyl-CoA that we have in our fatty acid molecule. That is, of course, taking the number of carbon atoms and divided by 2, which is what we do right here. And we get what exactly? We get 6, because 12 carbon atoms divided by 2 equals 6. So we can just write it right here. 12 carbon divided by 2 equals 6 acetyl-CoA molecules that we need in order to make this fatty acid right here. And then the final formula is a lot easier than what we did with the beta oxidation round. It's just taking the number of acetyl-CoA, multiply it by 3, and then take -1. And why we do this exactly, I'm going to explain. First of all, let's calculate it. 6 times 3 equals 18. And then 18 minus 1 equals 17. So 17 ATP, not ATP, yes, ATP in total, in order to transport and transform the acetyl-CoA, which we use in our fatty acid synthesis. Now, why is it times 3 exactly, and why do we have this -1 in the beginning or at the end? First of all, remember how the acetyl-CoA is transported from the matrix of mitochondria into the cytosol. We use this citrate shuttle, and then we lose 1 ATP right here. And for the citrate to go back into pyruvate and back into the matrix, we use another ATP here. So in total, we use not 1, but 2 ATP molecules for every acetyl-CoA we are transporting from the matrix of mitochondria into the cytosol. And this doesn't matter whichever fatty acid we're creating, it's always 2 ATP per acetyl-CoA. But then shouldn't we just take times 2 here? Where did the times 3 come from? Well, if you remember, in order for us to make the fatty acid, we need to transform the acetyl-CoA into malonyl-CoA, or else they won't be able to match together like this to create a bigger fatty acid chain here. And this is because the ACP can hold an acetyl-CoA in its right arm. I do I'm paraphrasing here, but and then for the malonyl to be introduced into the acetyl-CoA, this is just a transformed acetyl-CoA. For that to happen, we need to use another ATP right here. And that is used in order to make this malonyl-CoA molecule. So for every malonyl-CoA molecule we pretty much add in 1 ATP, because that is how much we need in order for the acetyl-CoA to be converted or transformed into the malonyl-CoA. So that is why not only does it take us 2 ATP per acetyl-CoA for the transfer of acetyl-CoA, we also need to transform it into malonyl-CoA, and that's why we add 1 here, and that gives us a total of 3. And then this -1 is due to the fact that here on this guy's right arm, we have a normal acetyl-CoA. Our very first acetyl-CoA in the fatty acid chain that we're making does not need to be transformed into the malonyl-CoA. It's perfect as it is in this little guy's right hand. So that's why we're not wasting an ATP here to convert it into malonyl-CoA like we're doing with every subsequent acetyl-CoA. We're just using this normal acetyl-CoA without transforming anything, and therefore we're taking -1, because one of the acetyl-CoA doesn't need an additional ATP in order to be transformed into the malonyl-CoA. Okay, So here we calculated, of course, we did follow this formula and we got 17 ATP, and that is what we got right here. ATP used solely on transporting acetyl-CoA from matrix of mitochondria into cytosol and transforming into malonyl-CoA. However, now we need to calculate the potential ATP that we could have had if we used the 6-acetyl-CoA in the citric acid cycle instead of using it in the fatty acid synthesis. So in the citric acid, we use it in order to create energy, right? And now you should know this by heart already, but for every acetyl-CoA we feed into the citric acid cycle, we get 10 ATP in total. So if we have 6 acetyl-CoA that we're using, which we know by this scheme right up here, we have 12 carbon atoms. That means that we just take 12 divided by 2, and that equals to 6 acetyl-CoA right here. So for every acetyl-CoA, we're losing 10 ATP potentially. 6 acetyl-CoA means we're losing 60 ATP. So this is the potential ATP loss from acetyl-CoA being losing its chance to be used in the citric acid cycle. And then this is the ATP used in the reactions and acetyl-CoA transport. And it's 77 ATP in total. This is a very, very big amount for just making a very tiny, sort of almost insignificant molecule by the grand scheme of things. However, again, we're only doing this if the ATP amount in the matrix of mitochondria right here is already too high and we're just accumulating acetyl-CoA. So if it's too high up here for ATP, we're going to use citrate to transport the acetyl-CoA from the matrix of mitochondria into the cytosol. And this is done in order to sort of deplete the acetyl-CoA concentration from one side into the other. All right, next up is regulation methods for fatty acid synthesis. So number one, the biggest inhibitors of fatty acid synthesis is of course glucagon and epinephrine, which would phosphorylate acetyl-CoA carboxylase. And what did acetyl-CoA carboxylase do? It's of course the one in the carboxylase reaction. It's the one that transformed the acetyl-CoA into the malonyl-CoA. So the glucagon pretty much phosphorylates this acetyl-CoA carboxylase, which inhibits it, pretty much saying that the acetyl-CoA is not allowed to be transformed into the malonyl-CoA. And therefore we can't make this fatty acid chain as we promised, because we can't just add 2 acetyl-CoAs and make one fatty acid chain. It's not how it works. It needs to be malonyl-CoA. But for activators, it's actually citrate accumulation. And we know this with what I said. If we have a citrate accumulation, it will take the acetyl-CoA and transport it into the cytosol. As for the regulation of beta oxidation for fatty synthesis, of course, we want to inhibit beta oxidation when we're doing fatty acid synthesis. Why? Because we don't want to break down more fatty acids when we in reality want to make them, right? Why break a cake if you want to make a cake? Wow, such a good metaphor there, Nadia. Everybody's gonna love you. Anyways, we really want to silence this in order to make more fatty acids. And therefore, an inhibitor to silence this, which would help increase fatty acid synthesis, would be malonyl-CoA. And the malonyl-CoA not only helps with adding into the fatty acid chains right here. Oh, here we can see perfect. This is a perfect explanation of how this looks. So this first thing is an acetyl-CoA. It's our first acetyl-CoA. It's this guy right here. While the subsequent technically acetyl-CoA are also our malonyl-CoA. But the malonyl-CoA also helps not only to add into this fatty acid chain, it also tells beta oxidation to stop working in order for us to preserve the fatty acids that we're actually creating. So that's all for the fatty acid synthesis regulation. Next up is the tag synthesis. And for the tag synthesis, we need to create one thing, and that is glycerol 3-phosphate. And the glycerol 3-phosphate can be created in one of two ways, either with the use of glycerol and 1 ATP by glycerol kinase, or with the use of the glycolysis, where we're creating this DHAP molecule or dihydroxyacetone phosphate, and using NADH plus H and glycerol 3-phosphate dehydrogenase in order to create this glycerol 3-phosphate. And this is what we use majority of the time. This is what we use occasionally, even though this is more energy conserving because it only uses 1 ATP instead of using 2.5 ATP. We're actually using this more often. This also goes to show exactly how it works. Pyruvate goes into oxaloacetate, phosphoenol pyruvate, dihydroxyacetone phosphate, and then finally into glycerol 3-phosphate, which can go into tag synthesis. Now for the actual tag synthesis, we're having this glycerol 3-phosphate at the beginning. And then for every acetyl-CoA that we're adding, we're actually using ATP and AMP. Remember, if we get AMP in the end, we're actually using 2 ATP per rounds. And this in order to create this final product, which is the phosphatidic acid. And the phosphatidic acid is used up here. This is the phosphatidic acid right there. And this one is used in the following reaction in order for us to make tags. It can also be used for glycerophospholipids, but mostly it's used in order to synthesize for tags. And the enzymes that you should know is acetyltransferase, which is also used in order to convert this phosphatic acid into the tag. And then also the phosphatic acid phosphatase would be good, but you can remember it as lipid as well. Now the number of ATP used for tag synthesis, it would either be 6.5 or 5 depending on what sort of method we're using. So no matter which fatty acids are attached to the tag, the only thing that takes ATP is the act of attaching the first 2 fatty acids to the backbone. The tag backbone is a glycerol molecule. However, the substrate used to create the backbone is glycerol 3-phosphate, since the phosphate group helps facilitate the 2 fatty acid chain attachment. So that's why we can't just use this glycerol molecule and add the fatty acid chains into it. We need the phosphate group in order to add in our fatty acids much easier. And this is more of a repetition of what happens. We of course have AMP here and AMP here. What does that mean? That means that instead of just 1 ATP being used, we're using 2 ATP up here and 2 ATP up down here. So in total that would be 4 ATP. That's only in order for us to make the phosphatic acid from the glycerol 3-phosphate, right? So that is common for any sort of method that we're making tags in. We're actually losing 4 ATP just because the ATP here turns into AMP, the same thing right there. But then we go into the 2 different optional ways in order for us to actually make the glycerol 3-phosphate, which is fed into the phosphatic acid. So remember what I said right up here. You can either get glycerol 3-phosphate from glycerol or from dihydroxyacetone phosphate. And dihydroxyacetone phosphate uses NADH plus H plus, while the glycerol uses just an ATP. So for the first option, we're using either 2.5 ATP, which gives our sum to 4 plus 2.5, which is equal to 6.5. And where do we get the 4? We get it from here, remember. That's when we're done with doing the glycerol 3-phosphate, right? But here, this is in order to make the glycerol 3-phosphate. In order to do that, we're using NADH plus H plus here. However, for option 2, we can make the glycerol 3-phosphate just by normal glycerol, and that is just by using 1 ATP, which would be 1 ATP for this. I am not awake today. It would be just 1 ATP in order to make this glycerol 3-phosphate. So 4 plus 1, that looks like a multiplication, plus 1, that equals 5 ATP in total. So it's either 6.5 ATP or it's 5 ATP, depending on which option you take to make the glycerol 3-phosphate. Yeah. Now we finally get into protein metabolism. This is the last thing that I'm going to go through with you guys today. So protein metabolism, of course, it comes from dietary protein, which we ingest, and that is broken down in our intestines or even our stomach by a myriad of enzymes, which we mentioned in colloquium 1, I believe. Yeah. And then they are created into amino acids. Now, these amino acids can get into the liver, and I also think that they can go into other cells, but the amino acids are then broken down. Like if we don't need this amino acid, we need to somehow break it down and excrete it from our body, right? But the only issue that we have here is that the amino acid contains something called ammonia. And ammonia is very dangerous to be left inside the body. So we can't just cut these up and then allow the ammonia to be free in the body. We somehow need to package this very, very carefully. We can almost imagine it as a bomb of sorts. We need to make sure that this will not be exuded into the body and create a lot of issues for us, because if you know anything about phenylketonuria, for example, which is an increase of amino or ammonium in our body, it can create a lot of complications, including impaired intellectual ability, gait abnormalities, growth abnormalities, etc. It's just not a good thing for the ammonia to be left free in the body. So that's why we need to transport it in the safest way we can. So we start with transamination, and for that we need 2 reactants, amino acid and alpha ketoglutarate. And if you remember this comes from the citric acid cycle, which we can see right here. So the alpha ketoglutarate right there. And they create, in turn, alpha keto acids right here, and then this amino acid right here, the glutamate. And the glutamate helps carry this additional amino acid into the cell, and it sort of helps with getting rid of this ammonia when it transforms back into alpha ketoglutarate. Because inside the liver cells, the ammonia can be released in order to be excreted into the urea. This glutamate right here with the additional ammonia is reacting with this glutamine. Now, the difference between the glutamate and the glutamine in my head is that the glutamine contains not one but two ammonia groups, while the glutamate only contains one. So when these react, they sort of get rid of this ammonia right here, amino groups, not ammonia groups. But this ammonia is created and then it is transported into the urea or uric cycle, which can occur inside of the liver. Here we see this reaction in more detail, which is this right here. And it contains the alpha-ketoglutarate and amino acid being converted into glutamate and keto acid by the aminotransferase. And it's very easy to remember this enzyme. We're transferring an amine group from one amino acid into the next. This reaction is in order to make the glutamine. So the glutamine is a very special molecule. This can pretty much be transported anywhere in the body, and usually it's transported back into the liver so that we can get rid of this amine group by the urea cycle. And in order to do this, you need it to react to more glutamate, and the glutamate will be able to release this ammonia into the urea. Now, this is an overall scheme of how it looks like. So you can see here, glutamine comes from extrahepatic tissues. It pretty much helps with transporting these ammonia or amine groups very, very safely. It goes into the liver cells. This is where the ammonia is pretty much regulated, almost like a very, very safe hospital, you would say. And then the glutamine reacts with the glutaminase to create the glutamate, and this also releases the ammonia, and the glutamate will continue to release more ammonia by glutamate dehydrogenase in order to be converted back into the alpha-ketoglutarate, and the ammonia here will be transported or will react with you can see here bicarbonate atom as well as 2-ATP in order to create this carbamyl phosphate atom that looks, or atom molecule that looks like this right here. And this is where we get into the first step of the urea cycle. So some things before I get into this exactly. Aspartate is made from oxaloacetate using a conversion from oxaloacetate into alpha-ketoglutarate, but also into aspartate. And this is used inside of the urea cycle a lot as well. Now, an easy way to remember the urea cycle I've noticed is that a lot of the components in the urea cycle kind of mirrors what happens in the citric acid cycle. And what is another interesting thing is that Krebs, which, the citric acid cycle is named after, the Krebs cycle, actually also sort of found out about the urea cycle, and he realized that these two, the urea cycle and the citric acid cycle, are actually intertwined. This is what we call the Krebs bicycle. So bi means two, so there are two cycles that we're focusing on, and they are somehow linked, and I will explain that in a second. But first, remember the carbamyl phosphate sort of acts as the shuttle of ammonia. It takes on the ammonia that is released from the glutamates and the glutamins inside of the liver, and it is going to react with this ornithine molecule right there. Now, ornithine is sort of created by arginine, but I would equated the best with oxaloacetate right here. Remember that oxaloacetate reacts with acetyl-CoA in order to create citrate? Well, in this case, you can compare oxaloacetate with ornithine. It also starts with the same letter, so it's easier. And the acetyl-CoA with the carbonyl phosphate as well. So here, just like oxaloacetate reacts with the acetyl-CoA, here ornithine reacts with the carbonyl phosphate in order to create what exactly? Well, citrulline. And see here, the oxaloacetate here reacts with the acetyl-CoA to create citrate, while here it's used to create the citrulline. So this is a little bit easier of an easier way to remember. Citrulline also has 3 amine groups, 1, 2, 3, and 4. Actually, 1, 2, 3, 4, 5, 6, 6 carbon atoms. 1 here, 3 here, 4 and or 5 and 6 right there. Now the citrulline will continue on into the urea cycle, and it will react with ATP. So we know this enzyme will be some sort of synthetase because we're involving ATP, and we're also adding the citryl AMP intermediate, and we're adding aspartate in order to make this big molecule known as an arginosuccinate. And remember, succinates we also have right here. So again, this whole urea cycle mirrors a lot of things that are happening in the citric acid cycle. I don't think you need to remember this molecule, nor do you maybe even need to remember the big how it's spelled out fully, but this is only a scheme to show you exactly what is going on here. Also, the aspartate right here, excuse me, comes directly from the oxaloacetate. Remember, the oxaloacetate we can find inside the citric acid cycle because the citric acid cycle occurs in what? The matrix of mitochondria. And here, instead of oxaloacetate going in and reacting with the citrate and acetyl-CoA, it kind of skips a lot of parts in order to make this ketoglycerate immediately and to make this aspartate. And this aspartate goes instead inside of the urea cycle to make this arginosuccinate. Now the arginosuccinate is sort of almost ligated by this arginosuccinase right here. And in addition to that, we're also releasing fumarate. And where do we recognize fumarate? Again, from the citric acid cycle. So after the succinate, just like we have right here, arginosuccinate, we release fumarate, which we do right here. Now this fumarate can be later used inside of the citric acid cycle. We're left, however, in the urea cycle with arginine. Now the arginine is not hydrolyzed, but hydratized, I think, with this water molecule in order to finally make this final waste product, and that is the urea that can finally be excreted from via our urine away from our body. And this is made by arginase, and the arginine will then be converted back into ornithine, and then ornithine can go back into the matrix of mitochondria. As you may have noticed, the first step of the urea cycle is done inside of the matrix of mitochondria. Meanwhile, the other subsequent steps are made in the cytosol. So the ornithine comes in, reacts with the carbonyl phosphate, and it creates the citrulline. So this all occurs in the matrix of mitochondria. This occurs in the cytosol. I think that's it, and all I wanted to talk about in regards to this. I will also be sending a copy of this whole document as well. Additionally, I haven't gone through anything from lecture 5 or 6, so please go through that before you start or during your studies. But there are no real pathways that you have to learn there. It's more about remembering where specific substrates come from, such as hormones, as well as different hormonal groups, pyrimids, purines, nucleotides, etc. But other than that, I hope you guys enjoyed. Good luck on your colloquium and see you next